This webcast talks about the problems in Worksheet 9b, which deals with electric charge and Coulomb's law. The first problem talks about two scientists who are having a dispute about a piece of dust and what the charge on it is. So Maria claims that it has a charge of 2.4 times 10 to the negative 19th coulombs, and Richard disagrees. He thinks the charge is 3.2 times 10 to the negative 19th coulombs. And so we need to decide who to believe. So I think the thing we need to remember is that charge is quantized. It occurs as integer multiples of the elementary charge, e, that lowercase e. And so let's just check. So here's Maria's claim. She says it has a charge of 2.4 times 10 to the negative 19th coulombs. So that must mean that the excess, or that the number of electrons it has lost would be that charge. And I said lost because she thinks it has a positive charge. And E is 1.602 times 10 to the negative 19th. So if I did this 2.4 e to the negative 19th divided by E, I get 1.5. So this is not possible because the dust particle cannot lose half of an electron. It can lose one electron. It can lose two electrons, but it can't lose 1.5 electrons. Okay, let's just go see if Richard's claim makes more sense. So he thinks that the number of electrons lost is 3.2 times 10 to the negative 19th divided by the elementary charge. Oh, and we get 2. So that is possible. So Richard is most likely correct here. Okay. What about if you had an apple and an orange? The apple has a net positive charge of 3 times 10 to the negative 17th coulombs. The orange has a net negative charge of negative 3 times 10 to the negative 17th coulombs. So can we determine which one has more total electrons? You might be tempted to say that the orange has more electrons because it has a negative charge. So it must have more electrons than protons. But that's not really true. I'm not sure that we can decide here. The net charge only tells us whether an object has more electrons or protons, right? So I could definitely say that the orange right now has more electrons than protons, whereas the apple has more protons than it has electrons. But the net charge does not say anything about the total number of electrons. So, I don't really know whether an apple has more or less atoms than an orange. All I know is that this particular apple must have lost some of its electrons, so it now has a positive charge, currently it has more protons than electrons, but I don't know how many it has of either of them. And I know the orange at some point must have gained some excess electrons because it currently has a net negative charge. But that doesn't tell me anything about the total number of atoms or protons or electrons that it has. Let's look at number 3. Here we've got one atom of a stable isotope of beryllium, and they're telling me that this atom has 4 protons, 5 neutrons, and 2 electrons. So what is the atom's charge? Well, I know that the charge equals the number of protons minus the number of electrons. So that must be 4, since that's the number of protons, minus 2. So it has a charge of plus 2 elementary charges, right? It has 2 more protons than it has electrons. So this atom has a positive charge, but that is measured in elementary charges, lowercase e. That's not coulombs. So if I want that charge in coulombs, I have to take that charge in terms of the elementary charge and multiply it by what the elementary charge is. And actually, maybe I should write it like this. So it's 2 times 1.602 times 10 to the negative 19th. That's the elementary charge, that lowercase e. And so this must be a positive 3.204 times 10 to the negative 19th coulombs. How many electrons would this atom need to either gain or lose to have a net charge of negative 1e? Okay, so right now it has a charge of plus 2e. It has 2 more protons than it has electrons. Negative 1e means the atom has 1 more electron than it has protons. And the number of protons does not change. I mean, if the number of protons were to change, we wouldn't have an atom of beryllium anymore. It would be a different kind of element. Okay. So it currently has 2 more protons than electrons, but I need to move it to the point that it has 1 more electron than protons. So it has to have 5 electrons to have a charge equal to minus 1e. Since it currently has 2, it must gain 3 electrons. That's how many electrons it has to gain in order to change its charge to minus 1e. Let's look at number 4. We have a balloon that has this initial negative charge. This is kind of a hard number to read. It has a lot of zeros, so I'm going to put that in scientific notation just so that I don't make a mistake in how many zeros I write. So I see 1, 2, 3, 4, 5, 6. That's e to the negative 6 coulombs, or negative 3.86 microcoulombs. Okay, how many electrons have to be removed or added to change its charge to a positive 5.86 microcoulombs? So first I need to find what would be the change in the charge of this balloon if And so that would be the final charge minus the initial. So the final charge that we want is 5.86 microcoulombs, so that's e to the negative 6. Then I'm going to subtract the initial charge, which is a negative 3.86 e to the negative 6 coulombs. And so let's find that. And so I get that the change is 9.72 times 10 to the negative 6 coulombs. Okay, so that's the delta Q, but I want to find the number of electrons. So since the change in the charge is positive, it's becoming positively charged. It was negatively charged at the beginning, so the balloon must be losing electrons, right? Because every time it gains an electron, its charge becomes a little bit more negative. But this charge is becoming much more positive, so it must be losing electrons somehow. And I can find the number of electrons because that would equal the change in the charge divided by the elementary charge, right? It can only lose whole electrons because charge is quantized. And so if I divide how much the charge has changed by the elementary charge, then I'll get the number of electrons. And so let's see. So 9.72 times 10 to the negative 6 divided by our E is 6.067 times 10 to the 13th. It has to gain, it has to lose that many electrons in order to have such a positive charge. Let's look at number 5. A scrap of plastic wrap initially has a charge of negative 3.56 microcoulombs, and then it becomes positively charged, and it's 18 centimeters away from a scrap of plastic. So, will the sock attract or repel the plastic wrap? Well, one of them is negative, and one of them has a positive charge. So, because they have opposite charges, they will attract each other. Okay, and then we want to find the magnitude or the amount of the electrostatic force between them. So we're going to use Coulomb's law, which says that force equals Coulomb's constant times the absolute value of the first charge times the absolute value of the second charge divided by the distance between them squared. So K is 8.99 times 10 to the 9th. Hopefully you've stored that in your calculator. The first charge, and I'm just ignoring the negatives, right? It's 3.56 times 10 to the negative 6, because micro means 10 to the negative 6. The sock has the charge of 8.37 times 10 to the negative 6 coulombs. They're 18 centimeters apart, but in this formula I have to put their distance in meters, and 18 centimeters is 0.18 meters, and I need to square that distance. And so I get a force of 8.268 newtons. And I'm going to stop here since this webcast is going so long, and I'll continue this worksheet in another webcast.